All right, so we're going to go ahead and get started. It is 10 after 10. So thank you everyone for being here. Allow me to introduce Dr. Susan Mantell. She is visiting us from the University of Minnesota, where she's been for 25 years.
25 years, yeah.
Got her prior degrees or graduate degrees from Stanford University. Right?
Yep.
And she's going to talk to us today about her work with dental composites and the work that some of her lab, or that her lab has done. So thank you for, again, being here and for your attention.
Thanks, Devin. I'm really happy to be here. Devin didn't explain that I actually know him from a long time ago, too. He and I worked together on a class. He was a TA, maybe a couple times with me. It's always fun. And I picked this topic. I thought, oh, I'll pick something that a lot of people can relate to. Also, it kind of highlights some of the things that we can do because we have a dental school, a medical school, a vet school. There are other ways that we can collaborate. So it's kind of a fun collaboration with the dental school. They actually have a chewing machine. If you go up there, they've got this, it looks like an MTS machine, and then their teeth, and they squirt some kind of saline solution, and then they grind, and they also listen for crunchiness. They once did some experiments for crunch in cereal. So they do some really fun projects. And my collaborator, Professor Folk, is actually a mechanical engineer, but he runs this dental research lab. So often we collaborate. And the student who worked on this, Lauren, it's a master's project. So I thought that would be kind of interesting too for you to sort of see what kinds of things we can do, you know, with the master's degree. Pretty fun stuff. So hopefully not too many have fillings here, but if you have had a filling recently, then they do this, and it's actually, I had kind of said it was UV light, but it's not. It's visible light now. I think I did a little bit of reading since I sent in the abstract. And so my side of things is not the dental side, more on the mechanics side, but there were some problems with UV light, but they use visible light now, and it cures very, very quickly. And that's what you'll see is that it's a polymer that has a photo initiator in there. There are packed with these tiny spheres. They can be nanometers, micron size. They're very, very small. I think the packing is like, 70%, some ridiculous amount of small glass spheres in there. And people like it because it matches your tooth color, that sort of thing. And it's been out there for a long time. And, nothing is perfect. So it is much better than the amalgam fillings that people had before. And people call them, they don't like to call them fillings anymore, by the way. They're restorations or something like this, but I might slip and call it a filling. So shrinkage stress can cause lots of problems in terms of, obvious things where the filling interfaces with the tooth. But one of the bigger things that we were worried about, and this kind of fits nicely in mechanical engineering, is fracture. So what happens is when that polymer in there cures, it shrinks a little bit, and it causes stress on the tooth. And that stress leads you to, you can have a fracture of the tooth. And so we have, people quantify how much stress it takes for fracture to occur. And what we wanted to do was try to watch how the stress evolves in that 60 seconds. So, the 60 seconds of cure turns out to be critical to whether stresses evolve in a way that lead to fracture. And here's a little bit of engineering. So that's sort of the dental side. Here in this picture, you're looking at, there are different ways that people try to study these things as an engineer, right? And this is a digital image correlation. Has anybody ever, I'm not sure if you do anything here with that, but basically think about it. This section right in here is represents the filling, and then it's actually a groove that's in aluminum. So it turns out that some of the properties of aluminum are similar to your tooth properties. And so when we as engineers are trying to do something, it's really a pain to work with real teeth. You have to write for, exceptions because they're human parts, even if they're from cadavers or whatever. So we try to do a lot of experiments with aluminum before we get to the teeth part. And so here they just put a groove in, and then you speckle it. And if you look at this, you say before and after, I don't see any difference, right? But video imaging can allow you to, so there's a video camera, this is the curing light. So what they're doing is looking at how this filling material changes during the cure, and you can track the strain. So what it is a video image. It looks at the speckles, right? And it looks for the pattern and then tracks where a speckle moves. And where the speckle moves, doing computer analysis, gives you the strain. And so you can get this real-time strain data. And it's, you know, there are very expensive systems to do this, but we just do something in my lab. This is not my labs. This was over at Folks, but we have some other experiments that we're doing with large deformation, and we do the same thing. We downloaded a MATLAB program from the web. We totally did it on the cheap. Normally, it's about $50,000 to buy the equipment. I think we spent about $5,000 between the camera and a few other things. So anyway, it's a really cool technology. People do the same thing when they're watching fluid flows there. They put particles in the fluid flow, and then they have a video camera and they watch where the particles move. So people in the mechanics area decided that they could spray paint plastics, right? And the trickiest part of the whole thing is getting the lighting right. It's just like a photographer's nightmare. You have to get the lighting right, you have to get the focus correct, and then the computer processing part is pretty much canned software that you can use. So that's just an example, and you'll see later I have some data for strain. All right, so again, getting back into the engineering side of things. So the Young's modulus is key, right? Remember somewhere you had something like stress is equal to the modulus E, like alpha delta T, something like this, right? Okay, so instead of a temperature change that causes strain, you have a shrinkage. So that's like, we call it cure. So as the resin cures, you have a delta cure, and then the modulus then becomes important too, right? And so here what we're trying to just show, I'm so not used to having the slides like behind me, and the picture here is really small. Can you give me 1 second while I change my view completely, because it's really bugging me. There, now I can really see it. Okay, so here what we have is, you're just looking at the Young's modulus, get an idea, okay, so what's the Young's modulus for steel, like 200 gigapascals. For these materials, you know, a peak is about 10 or 11 gigapascals. So, you know, what's the Young's modulus for aluminum? You know, we're pretty much getting close there. It's not as bad, right? So here, the real Young's modulus is this black line, let's just say. So that's a typical Young's modulus for a dental composite. Here's your time scale, right? You know, 0 to 100 seconds, you're done. You're up there. So what do you want? It's always good to know what you want, right? This is what you have, this black line, right? The goal is to not have any cracks in your tooth. So the ideal situation is something that evolves really slowly over time, but that wouldn't be really good, you know, in terms of you keeping your mouth open and they shine the light and you're waiting for this to cure. And this is, you know, the steep is not so great. If it goes too fast, then you really get the stress. So what we're trying to do is, if we can come up with a model, like, so our job as engineers is to kind of figure out an equation for this thing, right? Then we can do some analysis. So we use finite element analysis to look at how the stresses evolve, change, like you can change things about whether you cure it like one little layer at a time. Imagine like somebody put a little bit of this dental stuff in your filling, cured it, put a little bit more, cured it. You can play around analytically if you have confidence in your model, right? So our goal is to figure out how we can characterize this modulus as a function of time, and then we'll do some case studies looking at, hey, if we change how we shine the light or change certain things, does that, mitigate some of those stresses, all right? So that's kind of what I'm saying here. We get big shrinkage stress. So this is stress, not modulus, all right? So we just got done with the modulus that's like 10 gigapascals. This is about stress. So if we look at the stress between the tooth and the filling, we want it to be a number like well under 100 megapascals. So that's kind of our goal. In order to do that, we're going to figure out the modulus as a function of time, and we're going to make sure it's correct by comparing it to some data, right? And then we'll do some studies, okay? So, all right. So how do we do this? And there's a thing called a tenseometer, which people developed just for dental composites. So I doubt you have anything here. And it's about like, I don't know, bigger than a bread box. It's about, you know, this big, sits on a table, it's kind of heavy. But basically what it is, there's this big cantilever beam up top. So this thing is a cantilever beam. This is an LVDT. You guys all know what an LVDT is? Linear velocity. Okay, it measures displacement. So if it slides back and forth, it's an electronic measurement. You get like this change in voltage, and that translates directly to change in resistance. You get a change, some electronic change, and it translates directly to displacement. So you can get it to measure really, really tiny things. So what is happening here? All this stuff, so that part right here that's in the red box is still about this big, okay? The composite part right in there with the spring and damper, that's about like 4 millimeters or 5 millimeters. Okay, so what you're trying to do is, your composite is in here. There's some glass rods. That's to kind of give it kind of a stiffness. You know, ever done something in mechanics where you say, you know, the end conditions are fixed, something like that? That's the role of the glass rods, okay? So the glass rods are really rigid. The plastic is in here. The composite's in there. It's going to shrink, all right? And when it shrinks, there's going to be like a little displacement out here that gets measured. And this is how we figure out like how much shrinkage is happening, all right? And then there's some other experiments too, but basically that's one way you can get the data. That other experiment that I showed you with the speckles, that's how we get like how much stress is happening at the walls, all right? So that's like a totally different thing that we'll see later, but I just thought I'd throw that in somewhere because I thought it was a cool picture. All right, so right now we're talking about getting the modulus. Okay, you're here, it's a class. This is my one contribution to your education, these equations right here. Okay, so we're not gonna like go through them in gory detail, but a couple things. So basically, this is what's happening. This cylinder that you're looking at right there, that's the composite. This is a weird thing. I've never seen anything like it before, but it makes sense to me. So that K, that little K represents the stiffness of the equipment. And it turns out that basically there's this, the composite is doing all the shrinking, okay? It's doing all the shrinking, and how much it can shrink depends also on how much resistance it feels from the equipment. And because it's shrinking so little, you actually have to keep that in mind. Like normally, if you have a lot of shrinkage, then it wouldn't matter so much. But because of the relationship between the two, you had to keep all of that in mind. So think of it like you've got this thing shrinking, this other spring, and this wants to shrink, but the spring over here is stiff, preventing it from shrinking, right? Like it's not free all by itself to shrink as much as it wants, all right? It's like it's over here, but there's this other stuff that is kind of preventing it from shrinking. And so you have to keep track of that if you want to get to the composite shrinkage, the number you need, okay? You know, in order for us to figure out the modulus, I really don't want all that equipment stuff in there, right? So in order for me to do it, I have to account for it somehow. So this is just some mathematical things at the end, but you can see it's not super complicated, right? Spring damper system is something that you've seen in physics before. So just imagine, you know, it's in series. And that's really what this is telling you. It's in series. This is saying that all the strain, you know, you've got a little strain from one spring, you've got some strain from the composite, you have some strain. Get to drop. So we are so lucky. You know, the damper shows up here, but we get to drop it because why? Because this thing is happening so fast that creep, you know, that idea when you put the load, it takes a really long time. That's not happening for us because by the time it solidifies, it's gone. So that makes our life a lot easier. And in the end, so bottom line, this is the modulus, and it's a function of how epsilon sub s, that's the shrinkage strain. The stress, what about the stress? Remember when a spring, when you have all these springs in series, what do you know about forces? The force is the same because they're all in series. So stress, in this case, is the same. You know, we can just divide by area and get a stress. So the stress is the same everywhere. So here, the stress is the stress of the whole thing, but the shrinkage strain, because we've done some mathematical things there, we can pick off the shrinkage strain that we need. And then a cross-sectional area, K, that was really tricky to get, the K of the equipment, and I could go into it, but I think we'll just keep moving, all right? But so, and then L has to do with the, you know, it's the little 4 millimeter thing. So, at any rate, okay. So what are you looking at here then? So we're going to have a lot of plots. And what we're looking at here then is time on, so I'll try to go through it each time. So what's kind of weird about this equation up here, do you see time there anywhere? Yet I know I want modulus as a function of time, right? And you don't see time in the equation anywhere, but it is there indirectly because the stress and the strain are both functions of time. And so from the tensometer, we get how the stress evolves with respect to time, okay? And then there's a totally separate test, unfortunately, that we have to do to get this strain as a function of time. So we can't do them both from the tensometer. That would be nice, but it's not normally done. We only use the stress from the tensometer. Here, I'm just showing you 3 different resins. You know, there's a bunch of different resins, but you can see that in the end, we'll show you that the modulus of one of these, I think the Z250, has like the biggest modulus, and some of these others have a lower modulus, and that influences what kinds of stress evolve. Like, what do you think? Okay, we'll take a vote because this will keep everybody awake. If your modulus, so before we get to the end, your modulus is really high, do you think that has a higher shrinkage stress at the wall than if you have a lower modulus? Not a trick question. Okay, raise your hand. High gives you more shrinkage stress. Yep, good. Okay, and if it evolves faster, more shrinkage stress. Okay, all right, so kind of like that's the theme through here. We will get there. All right, so we get these data. It's all with respect to time. More equations, but I'll just explain those in a minute. So basically now what you're looking at is strain versus stress. All right, so what we did was we took these data, right? And then we said, okay, time is in common, right? So we'll just put them together. And we can say, here's the strain versus the stress. We had this equation, and what I need in that equation is the change in strain with respect to stress. So I do some curve fit, and I'll explain what the curve fit is for strain as a function of stress, okay? So I've got A, B, and C, 3 parameters unknown that I have to curve fit for each material. So so ignore the bottom equation for just a second, all right? So I've plotted strain and stress, right? And I say to you, give me a curve fit. Could you do it? Sure. Should I pick a decent form? Yes, right? So what form did I pick? I picked something where, all right, there's some evolution, like some exponential decay, right? 1 minus E, that's gonna like sort of jump up and you'll get some decay. And then then A sigma gives me this linear part. So what it's sort of saying is I'm gonna have a linear part for some time and then I'm gonna decay for some time. So it's not like we just said, here, give me a 6th order polynomial and fit it to there, all right? And there was nothing magical about this, but there's some you know, history and background to what might be a good fit. So once we get these, so for P90, I get A, B, and C, right? For Z250, I do the same thing. So each resin, I can do that. I still don't have a modulus yet, right? But to get that modulus, I need the change in those. If I have this equation, I can take the derivative, and I can get another equation, but it's still just got those same constants, all right? So that's what we did to get this ratio. There's really no time in there. I still think that's a little bit weird, but it's in there indirectly because of how things evolve with strain and stress. So in the end, here is our Young's modulus as a function of time. So you can see we've got this P90 that sort of has a little bit of a delay and still jumps up. Everything goes faster than we really want. But it turns out that you'll see later, I don't have any data for the Z350, but the P90 is definitely gives you lower shrinkage stress than the Z250. And what happened was the dentists know this, okay? They already know like which things cause more cracking than others, but what they want to do is be able to play with it and try other materials. And so if we can come up with a way to like take some basic data and predict the modulus, then they can use that we can use that in other models to predict the shrinkage stress, and they can say, maybe the number isn't going to be exactly right. Okay, let's just say, you know, we're going to be close. They can say that one is better than the other. They can at least get a little bit closer than having to do a lot of real experiments with teeth, because they can say, hey, I know a lot about these 3 resins, and now I've made a new one, and my new one does this compared to those. And they can use that to help figure out, you know, how much light they should shine, whether they should do it by layers, that sort of thing. Okay? All right. Okay, so now we're on to like, so how do we know if this works? There's a lot of stuff in this slide, but I just want to give you an overview, and then I'll break it down for each one of these. All right, so basically, we have those material properties, finite element analysis. Do you guys do any? Okay, what software do you use? You write your own? SolidWorks. Okay, SolidWorks is a finite element package that goes with it. Okay, good. That's good, because that makes it really easy. After you get the drawing done, you can just keep going. So we used a package, Abacus, which is, it's kind of, it has capability for people to write their own material properties. So I think in SolidWorks, you can probably give some properties, but here we can do some other things about how, you'll see kind of like, I made it really short and easy, kind of the algorithm we use to add up the stresses because they're changing with time. And we're not using like a typical, so I know you guys have had plastics, so we're not using like a viscoelastic material model. So we can't just like pull in viscoelastic material and give it some properties. We have to give it our own. I call it a constitutive law. It's just the relationship between stress and strain. So we can make any equation up we want and do that. And it's not rocket science. There's, you know, a lot of user groups and things that can help you with that. All right. So the first thing over here, and I'll go through it, but this one is how we validate and make sure that our modulus that we got was correct. The second one, this is basically that aluminum. Remember when I mentioned we use aluminum and we have a groove in the aluminum, right? So the second one, this is an not axisymmetric, but this is an axisymmetric model. That's actually a cylinder with the spring. Okay, that's the spring for the equipment. This one has symmetry. It's a quarter model. So there was a block, and we just modeled a quarter of it. And then this is the tooth, and we did axisymmetric. So, you know, 3 levels, right? Validation. These 2 are more about validation. Here, case study with some teeth. And there's some data with that too. All right, so quickly, what happens in the FBA model? So we have, what is this? I have E and alpha, right? So remember we talked about shrinkage. You're used to seeing shrinkage in terms of delta T, right? Change in temperature. And so we actually trick the computer code. Well, it doesn't really know, but we just tell it it's temperature when it's time. Okay, it doesn't know the difference, okay? And we do this incrementally. And so because there's some reasons why that that's totally a cheat, but you can do it, all right? So alpha is normally your coefficient of thermal expansion, but here alpha will be our coefficient of shrinkage. Then we use the delta T. And we have like an incremental load, right? So like you would normally do alpha delta T for temperature, but ours is pure delta T for time. And then we get out displacement and shrinkage, and then we keep incrementally adding it, okay? So we just, you know, run it for a little bit, then do a little bit more. And in this case, there's some ways to do this so that it's, we call it path dependent. So it it cares about where it's been before. So it needs to know, hey, I started at 0, now I'm at 10, now I'm at 20. So it's not like you can just, so you want to take information from your last state of stress and feed that in for the next state of stress, as opposed to like every one is just a separate problem. I didn't know that I was already at 10 megapascals. So I use that old information about the stress state when I add the next load, okay? So back when you're doing whatever finite element analysis, right? You have like boundary conditions and loads, and then you get out displacements. It's the same thing here, all right? We have a boundary condition that I'll talk about for each model, but the load is always this alpha delta T load, okay? So you could do that on your SolidWorks too, putting in alpha and a delta T. But what happens to us is because it evolves over time, we have to break it down into little increments. One of the things we found then, so I'm getting a little bit into the weeds here, but just a little bit about how this works. So remember that line, the red line represents the modulus as a function of time, right? Okay, So the modulus is changing at every instant in time. You agree? Except like when I get over to here, it hardly changes at all. It's pretty flat, all right? But when I get in this region right here, it changes really rapidly. And we had some data, and so we figured out, which it doesn't take rocket science to figure out, but it seems clear that the more steps you take in here, right, the better you're going to be at predicting the final stress state, all right? And especially because it depends on how you get there, right? So here, what people used to do is, so let's just say, see this gradient box? You just barely see that. I tried to shade it in, but I didn't know it would come up. But that gradient box represents a little delta t in time, right? Okay, and I have to pick out a modulus for that delta t in time, right? So I've got, you know, my modulus is changing huge, big amount in that box, right? That narrow delta t, I've got, like, I could pick a modulus down here or up top, right? So the narrower I make that, the better off I am, right? At like moving from this low modulus up to the top, right? The narrower I make that. What people had done before, so what happened was a dentist came to us and said, the stresses that we're predicting are just way too high. It's just impossible that they're that high. We don't see that. And why is that happening? So first we started with, you know, getting the E, which wasn't big difference from what other people had gotten from the data, okay? But then the next thing was, how do we do the modeling? And what they used to do was, in this narrow increment, they used to take this top one. They used to just go, okay, I'm here the step before, and the next step I'm up there. And believe it or not, you know, you'd think that wouldn't make such a difference, but what we did was we used that, in that increment, we used the average, which is like, you know, from integrating, you had like the trapezoidal rule, remember that? And like, you know, so, you know, we used the midpoint. And it turned out that that was significant enough that the stresses that we got were much more representative of what they were actually measuring, okay? So just like, you know, something really small like that. And of course, let me just say, it wasn't, oh, this afternoon we're going to decide to do that kind of thing. You know, it took a couple of weeks of trying a bunch of different things to figure out what might work, okay? All right, so here's where we did it then. If you're looking at, you know, finite element analysis, right, you want to do something that takes advantage of your geometry. So again, it's a cylinder. We use axisymmetric. We have the spring that represents the material spring. We put in our properties. We get out, we pin along the bottom boundary condition, and then we get out some displacement. The reason why it's pinned is why, because it doesn't just shrink this way, but it also shrinks this way radially too. Okay, so that's what we were doing. This is supposed to represent the tenseometer, right? Remember the tenseometer, the little glass rods and the round little cylinder, right? So that's what this represents. So this had better come out right, because we use the tenseometer to get the modulus. So hopefully when we try to simulate the tenseometer in our finite element, right, hopefully we're going to get a good match. It's not as great as I would really like, but it's pretty good. So, all right. So here, just ignore everything on the left. That's just showing the model, but the right is the data. So what you're looking at here, time. So again, evolution of stress. And the dots down here are experimental points. These are data points. And then our model is going to be the open. That's our current model. And here, earlier models. So we used our same modulus, but used the different approach, used that step approach, where even though in both cases, we took 15 increments, all right? So you remember how I showed you that plot, and I said I used only 2 over here, but 15 time increments. So they both had the same number of time increments. But the difference between taking the modulus at the end versus taking it in the midpoint is huge in terms of stresses. And it turns out that, you know, that we're pretty close. And what's this weird little bump thing here? There's something about when you cure it, the cure gets started, and then there is like an autocatalytic kind of thing that goes on. And so you'll often see that the light goes, but then there'll be some point where it's sort of self-perpetuating for a while, and that's why you get this kind of, starts to flatten out, and then all of a sudden that autocatalytic, where, you know, the linking, cross-linking just kind of gets going, will give you this secondary sort of jump, and then it kind of fizzles out once all the cross-linkings happen. Okay, so now I'm just going to show a little bit of the cuspal deflection data. So here, again, it's the groove, right? It's an aluminum block with a groove through it. It's symmetric. what does it mean to be cuspal deflection? What happens is we measure the deflection on this surface right here. Okay, so here, unfortunately, the image I have is all green, but this represents the filling, right? That yellow section, the composite, and the aluminum block is here. It's a quarter model. That's why we have symmetry on these two things, right? The load we apply is that alpha delta T kind of load. And then what we're going to do is track the displacement on this surface. All right, another wake-up call. Talk to your neighbor. Ask yourself, which way, if I measure displacement on that surface, which way will it go if it's shrinking? Pause. Ask yourself if you're awake. Ask a friend. Go ahead. Think about it. So will it move towards the middle or away? It's shrinking. Okay. Good. And now while you're doing that, where do you think the stresses are highest? Another question. Okay. So stresses, we're gonna look at stresses along the surface, and it'll be normal stress. So that means normal to the surface. You're gonna look at the top, the corner, and the bottom. So 3 choices. Again, think about it. Talk to a neighbor. Top, corner, bottom. All right. Okay. I just think that, I haven't given a seminar this long in a long time. And I know it's like before lunch. So it's good. And also it makes you think about what might come next, right? All right. So here we're looking at deflection. And yes, it deflects moves in, right? Because it's shrinking. So it sort of pulls that upper edge in, right? And you'll get more deflection up at this top corner than down bottom. So what happens is they have this thing with the groove, they shine the light, right? And they have a dial indicator. It's a little bit fancier than that, but basically an electronic readout. And we're recording how the side moves with respect to time. We just have to be super careful that we know exactly where that is so that when we're comparing our model with their data, right? We don't want to be at some corner that's like, we want to be actually more right at this middle point, right? Because then we don't have any of the edge effects too, so. At any rate, you can see that there's some experimental data, the triangles, and there are our model data, so it's pretty good, right? Why is it that we have just 1 point over here that's the experimental data? Actually, we only had data through here, and then what we did was we did some kind of interpolation, and there's more points further out, something like that, and that's how we got the last point. So I would say in doubt is how well this fit is, but the rest of this is pretty good. And then, I hope I have stresses. Yeah, I do. I knew I did it. Okay, so how many people thought it was in the corner? Yeah, the corner is always going to get you because stress concentration right there, right? And so I put this gray box on the corner. Here's the top. Sort of the little funny things going on at the top. This is only now, these are not data. This is stress, so this is just our model, okay? For this particular resident, I didn't want to go back through and try to find more data. I just wanted to give you a sample. But, okay, so you're running the model. We just pick off the normal stress, meaning perpendicular to this, where the interface is between. So it'll be in this direction, and then at the bottom, the normal stress is here, and then there's something weird happens in the transition. So I'm not exactly sure about this point, how we got that normal stress because we were in the corner. But you can definitely see a peak, right? And then it drops down, which is what you expect. But what's also interesting is the bottom, at the end of the day, right? The bottom has a pretty high stress compared to this top edge too, okay? And that's sort of, kind of what you think might happen, right? You filling in and it starts to shrink and it's going to try to pull away. And they do a lot of different things. So I'm not showing this here, but we reran the model with a different, like an epoxy, a very thin epoxy layer here, some kind of intermediate bonding material that goes between the composite and the tooth, right? So, sometimes they'll say, oh, let me prep the surface. And they put some kind of like adhesive thing. It smells a little different, but basically those things have been shown to improve the bonding between the two because you've got like sort of this mismatch in stiffnesses, right? And so that's kind of helpful too. All right, so then this these next few plots, I'll try to walk you through them. There's just a lot of dots on there. I didn't have a good way of cleaning them out, but let me just say, all right, so here's a tooth. And how do we get these tooth models? This is not just like, you know, I looked up in a textbook and drew it. Actually, some of my students are working on something like this right now, which is there's a CT scan over in the dental school. It's a really small one, not the big one like your whole body goes in. It's called a micro CT. And they CT scan the tooth, and they'll actually see, they'll be able to see when the we work with dentists, and they'll do a kind of study how they drill this location for the restoration. They'll try different kinds of tapers and things like that, and then they'll put the filling in, and then they want to look at stresses. So we use the CT scan to exactly model that, right? You can see the differences, and it's three-dimensional. It takes a lot of work. You take the CT scan, and then you have to kind of clean it up because there's noise, and you take that data and turn it into a finite element mesh. And so we actually haven't done that last step. Right now, we're just taking the CT data, but I've heard that cleaning out the noise is really challenging. So anyway, so that is how we get these tooth models. Is we get teeth, the dentist drills it out, we scan it, and then we actually use that. All right. And here, I wish this was a lot bigger, but all right. So let me just walk you through. So what we're looking at here is going to be two different resins. So just remember the P resin had a much lower stiffness, a lower modulus, right, than the Z's. All right. So P is going to be on the top. I hope I kept that consistent. I just have two slides like this. And what you're looking at here is we tried a couple different things. So first of all, the black dots, the prior models mean that's the one where they took the step too big, all right, where they took that modulus too big. And you can see that the prior model is always giving you a higher stress, all right? So here we're looking at radial stress, so it's only along this wall, radial, nothing along the bottom, okay? So what do you think happens, you know, at the top corner, right, at the top edge, it's low, and when you get to the corner, it's high, all right? So just like what we saw with that group, again, we're only going from here to here. We're not going along the bottom, all right? Then, so you can see prior models are higher than what we have here. And then the other thing that we did was we looked at different kinds of cure. Here, what we had done first was we had said, oh, we just shine the light and everything cures consistently. But that's not really true. The resins that they work with have they're a little bit opaque, right? So more light is at the top than at the bottom. And so if you cure that way, what happens is you can see the stresses when you've got it as a function of depth. Then the stresses are a little bit lower, and that's probably most representative of what's really happening in the system, right? It's not that you shine the light and everything sees the light the same, right? Stuff at the bottom doesn't see the light as well as the stuff at the top. And there's some data that we had so that we could figure out how to factor that in, all right? But I'm not showing that. And then, so the scales on these, unfortunately, this is even a bigger scale. This is 80, and the scale on the other one is only up to 60. So you can see this is a Z resin, and the Z definitely hits a much higher stress level, and also it seems to just kind of be plateauing, right? It seems like there's not a lot of difference whether you're at the edge, at the top, or at the corner. It's almost consistent all the way across, okay? And there, I didn't then bother to show what happens with prior models because we've already sort of generated. But think about this. This is where they've been in the past. And with the prior models, everything was failing. If we're peaking at 80, and remember I said 100 was probably the point where they start to really worry. The prior models were always going at 100, yet they weren't seeing failure with the Z resin. So that was kind of the beginning of why is this happening? We're predicting that it should fail. It's not, what was the problem? So I would say the biggest thing that we changed was just that how we integrated through that curve. Instead of taking that end of the step, we took the middle of the step, and that made all the difference. All right, so again, one point is definitely lower stresses if we consider that, the opaqueness of the material. If it's more transparent, then you won't, that would represent that single layer cure. And here then, I'll just walk you through this. Basically, here what we did, so that one was all along the wall, right? And here's just two locations. So it behaves the way you just thought, all right? Back when we did that group, what did we think? We had higher stresses at the bottom, right? That would be section 2. And you can see section 2 is much higher than section 1. And then again, I had 3 sets of dots up here for the P10, just because that was data that other people had done in the past, the dark dots, and everything that we've been working on are the lower things. And then again, the gray represents what happens if you say, hey, the light doesn't go all the way through. All right. And then with the Z resonance, you can see again a comparison. The scale here is up to 70, whereas with the P, the scale goes up to 50, and most of the stiffness, most of the stresses that we're seeing, are like less than about 35. Whereas here, with our model, we're seeing stresses that are 60 to 70. So again, the Z is much higher. All right. And so we would, most people have evolved to using some of these P resonance. Okay, quick conclusion, which is that, we use this constitutive law. That's where it all started from, is this the modulus versus time. We use the finite element models to make sure, kind of convince ourselves that things were working, comparing to whatever data we had. And then we went on to doing some case studies. And the lower stresses, theoretically, the time, we don't seem to have much control over that cure time. Once it starts to cure, it just goes. So the only other thing we can really control is the modulus. How low they want to go with the modulus is actually a concern, right? So it's definitely better to have a lower modulus, but not so great for your tooth. I mean, you can't just go, well, let me put some rubber in there then, because that will be less for stress, right? So there is this sort of balance that you have to hit. But other things that they can do then, and I'm not showing it in this study, but we went on to study sort of putting a bonding layer in there, so some kind of interface between the filling and the tooth to sort of mitigate some of the stresses. So once you sort of build your confidence with, hey, I know how to model the modulus as a function of time, then you can go and start adding little things like, a very thin layer. How thick do I make that layer? Do I shine a light and only cure a little bit on the bottom and put some more in? You can play with all those things. And this was just sort of the starting point. And so that's what a master's student did. It represents about a year of work. It's a 2-year thing, but the first year you're mostly taking classes, kind of learning how to run the finite element. And about, I would say, honestly, the last 3 or 4 months is about writing the thesis. It's so painful sometimes to write the thesis part. But if you can write papers along the way, it goes much faster. So that's usually in a master's degree, try to get like one paper. One paper from a master's degree is pretty good. And if you have that, you can kind of turn that into, you split it up among your chapters and it becomes your thesis. And this person was paid to do the work. It's part of, if you have a certain type of thesis, then you get a stipend and your tuition gets paid. So I can answer questions about that too. I just say I have 3 slides here, something about our department. I know that everybody's been to the Twin Cities. We just had the university president just visited our department on February 14th. So this is Kaler. He's a chemical engineer from the University of Minnesota. He's been our president for 6 or 7 years. And when he came 6 or 7 years ago, he said, I'm going to visit every department at the University of Minnesota. So it's been 6 or 7 years and he's visiting our department now. And he said he's halfway through. So anyway, so just kind of by the numbers, how big are we? And I think it's interesting because I just talked to Devin, and I think with all your teaching faculty, you might be at 40. And we're at 42 faculty, 63 staff. This is our master students and then PhDs. I would say, there are probably some part-time things in here too, especially, some PhDs, sometimes they're on like the 10-year plan, so it might be a little bigger than the number that are actually active. Undergrads, that number 536, we graduate, probably more important is how many we graduate each year. It's about 190. And again, the other numbers there. Research expenditures, that's a lot of money, but part of that is we have a few really big centers, and I'll just say a few minutes about that. But this is how many new faculty we've hired since 2008. So if you think about that, what is this? 6, 8, 15. 15 new faculty since 2008. We have 42, so a huge number of our faculty are new. We are, you know, if I did some plot versus age, which is probably not allowed, you know, we've got like the two extremes, and I think we'll be seeing a lot of these retirements in the next few years. And then research areas, you know, we're big universities, so we have heat transfer. We have a lot of interesting labs there. We do some things. We have a number of my colleagues do biology and biotransport. We also, aerosols and filtrations is something that's really big. TSI is a company that kind of came as a startup out of Minnesota like 50 years ago, some huge amount of time. Combustion and plasmas, these are nanodots that are used for solar cells. Fluid mechanics, we have a wind turbine, but we also have some facilities at the St. Anthony Falls lab that is where they study flow on these things. Fluid power is a big area. Transportation, so that's where I was saying, you know, we have some big centers. We have a vehicle simulator in our in one of the buildings. So it's like it's like if you walk down this hallway, you could go open a door and there's a car in there and vehicle simulator, and they work on things like keeping drivers awake, you know, the seat vibrates, things like that. Sensors and controls. Medical devices, we have a big center for medical devices that we collaborate with, but there's a home here in our department. And advanced manufacturing, we have a number of people who do manufacturing, but also 3D printing. I have a colleague whose degree is actually in chemistry, who does 3D printing things that are ears, heart, these kinds of things. And it's been a natural collaboration for him with the medical school. There's somebody who does, I just remember when he gave a seminar, there were pictures of rats with little PC boards coming out of their heads. And what that was he does craniosurgery where they can like precisely locate wires to probe what neurons are doing in the brain. So the mechanical engineering part of that is like drilling in and locating those wires, you know, and there's some feedback involved. It's very interesting. Okay, I think that was my last slide. Yeah. So I'm happy to answer any questions.
Thank you.
Yep.